this is the pump chamber. This is one of three. Inside it is a YAG rod. That's yttrium aluminum garnet, and that's the gain medium of this laser. That's what gives it its characteristic properties: wavelength, power, all that sort of stuff. It's pumped by some diode bars that are inside this arrangement somewhere. And there's a little circuit here for static ESD protection. Laser diodes are very ESD sensitive. And they take about 200 volts at 50 amps to run one of these pump chambers. So there's three 10 kilowatt power supplies inside this to drive all three of the pump chambers. You can also see up top we've got some sort of, it looks like a desiccator. There's a little air filter there and probably a desiccator up there. And then over here is some sort of sensor dangling inside the pump chamber. There's a board inside the control side of life that seems to monitor humidity. And it's reading high, so we need to make sure that if they seem to go into a lot of effort to control humidity within this, so we need to make sure that we can either dry it out, or if it's not a problem, we don't worry about it or something. You can see here on the front, I don't know if you can see, there's little water cool hoses. So that's all of the optics being water cooled. Inside these black boxes are optical assemblies that mix the three, that basically make a circuit out of the three pump chambers in series. So all the mirrors and whatever else that's in here will be water cooled as well. You can see all the cables and pipes and everything are very nicely routed under this shock mounted deck. This whole thing actually moves within the laser on big rubber grommets down there. The rest of the stuff that's up here is basically just plumbing and electrical connections. There's not a lot more to see that's going on up here, but this really is the heart of the laser. These are what make it into a laser, and that's what makes it so special and powerful. So obviously in a laser, you've got a gain medium and a resonant cavity. Those are the two things that make a laser go. In this case, we don't have three independent lasers that we're mixing together to form one beam. We have three gain mediums and one resonant cavity. So the gain mediums are effectively in series, but the resonant cavity starts here and ends over there somewhere. So the light effectively goes in a circuit through all this optical gain in order to make one big laser. It's tricky way to do it, but you get much better beam quality if you have one coherent amplified beam rather than three separately coherent beams that you're mixing together. You get smaller spot size and more power and all these good things that you get with coherent light. So just thought I'd mention that as well. Okay, so as I'd like to speak a little bit more in depth about what's up here, specifically these two fiber launches. The connectors here, they're a sort of standard high power fiber connector. I can't remember what it's called, but basically you plug it in there, and you also have to connect this. That's a water cooling loop, so that actually cools the fiber optic cables. There's another water cooling loop for them here. So it's all, it is literally all water cooled. The whole of the system is. This has a mirror in it, which can direct 40% of the light down the fiber optic cable, and then 60% either goes down here or to the beam dump, which is back here. This beam dump is also water cooled, so that can absorb 1.6 kilowatts of laser and do it all day, every day. This gives you either 60% or 100% out of this fiber. So there's two fibers that come out. You either get 40 and 60%, or 40 and 0%, or 100 and 0%. In terms of what happens at the other end, we don't have the fibers here, unfortunately. They're down in storage. But there's a small end effector, which is about that long, and it has a window at the end of it, which lets the light out, and that is a 10 millimeter diameter beam at 1064 nanometers and 1.6 kilowatts if you've got this thing turned up to What that can do, theoretically, if it's working and focused down to a point, it should be able to cut through 20 millimeter steel with the right conditions around it. So it's different to the lasers that we've used here for materials processing before. It's a different wavelength. It goes pretty much straight through acrylic, so you can't, it's a shortwave infrared, so it's 1064 nanometers. That's almost red. Red is around, you start seeing red at about 700 nanometers. So it's not very far into the infrared. The CO2 lasers that we use upstairs, they have output at 10.6 microns, so that's a much, much longer wavelength. That is mostly absorbed by sort of more organic molecules. This is absorbed very strongly by metal. So it is very much well suited to welding, cutting, etching, whatever, on metal. So yeah, that's the business end of the laser, you could call it. And this will be the bit that I run scared from when we turn it on, because if it works like it should, it could probably poke a hole straight through this lid.